Welcome to this lecture on continuum modeling. This is part of the lecture series on basics of mathematical modeling. My name is Timo Tiihonen and I try to introduce you some essential things of continuum mechanics and continuum mechanical modeling. Before going deeper, we will go through some motivating examples and discuss about systems and conservation principles on a general level. As an example, let's think about the balloon. It can be a helium balloon, hot air balloon, a balloon that typically rises when it's let free. Does it rise? Does it sink? If it rises, how fast it rises and how high it will reach eventually, and what happens during that process. Does it expand? Does it change its shape, and so on. Which phenomena are of interest when we are analyzing this type of balloon? So which phenomena have to be modeled, how they can be modeled, and what are the structures that are generic in these models. So these are the questions we will try to focus on in this presentation. The balloon has been chosen as an example because it's a clear illustration of a system that has clear inside, clear boundary, and clear outside. So balloon and its environment, they are sort of independent, but they are interacting through the balloon surface. So we have at least two different subsystems in our model, the balloon or inside of it, and the outer space, and maybe also the balloon surface, depending on what we will be modeling. In the scope of this lecture, we will speak of systems as clear entities that have distinguishable boundaries, and they have a distinguishable states. So they have an identifiable state, and that state will be changed through interaction of the system with its environment, and this interaction can be identified, can be recognized as clear inputs and outputs. So how the system communicates with the environment is sort of understood and modeled. Typically, when we are modeling some phenomenon, there are several subsystems, like in our balloon case, the balloon cover, exterior, and several input-output interactions between them. So these are the things that we actually model. There are different types of systems, so qualitatively different types. The subsystems, their interactions differ in respect to how they behave as functions of time, functions of space, and so on. There are systems that we call discrete. The characteristic feature is that their states are of discrete kind, so there are only finite number of different state values that are possible. This implies that also the time behavior is discrete. So if you are changing between two discrete states, outside these state changes, nothing interesting can happen in the system. So the time is naturally divided to discrete events that take place in some periods of, in some instances of time, and between these instances there are periods where the system is in stable state, so nothing happens in the system. Also, typically we have a finite number of subsystems, so the system cannot be divided to infinitely many different subsystems. Typical applications are different types of queues, containers, warehouses, and so on, where you are moving around discrete objects and counting them as a rule. Another type of family of systems is continuous time systems. Here the system components can have infinitely many different states, so that they have a sort of continuous state, a state that can vary continuously, and as this is the case, also the time is of importance at every time, so the time has to be treated as continuous variable, but still we have only a finite amount of subsystems, so the system cannot be divided to infinitely many subsystems of importance. Typical example is point mass mechanics, where we have a finite number of structural components that are rigid bodies, but they move continuously. So moving skeleton and so on. Also some containers behave like this. For example, if we are modeling say fluid containers, where the state is the level of fluid, that easily can be seen that it can move continuously, or it can vary continuously, like when the container is being filled, the level is changing continuously and we get the continuous time system. This typically lead to differential equations as models, mathematical models. And finally we have continuum systems, where we have infinite number of subsystems. It basically means that the system is a continuum that can be divided infinitely many times to smaller systems, and the states are continuous. They are infinitely many state values. Time is continuous. So this goes to continuum mechanics, fluid mechanics, heat transfer, and so on. Now returning shortly to the balloon, we can model the balloon in many ways. So if we are selling balloons, we can model them as a warehouse accountant, just counting them, and they are moving in and out from our warehouse or store and so on. So it's a discrete model. If you look at the balloon from far, it can be understood as a point mass. It's flying, rising in some way as a single point modeled by a differential equation. But if you want to be accurate in modeling, we have to consider it as a continuum system to get better view on what are the actual forces that make the balloon move, make it deform, and so on. So we have been discussing about systems on general level. Now we focus on another basic concept, which is the conservation principle. In the context of conservation principle, the system has one or several special properties which are called states or conserved quantities. These are properties that obey conservation principle. The conservation principle is something very simple. It only means that the change of state, change of conserved quantity, or actually the rate of change, can be explained by a few factors that can be identified: source and sink, or inflow and outflow. So we can clearly identify those things, those effects that actually change the state. This is rather generic, so very many things fit to this frame. We have separated source and sink from inflow and outflow to highlight that there are some changes in the state that are in some sense system internal. So they happen inside the system without the direct contribution of the system boundary. And then the flow terms refer to things that happen between the system and system environment through the system boundary. Once we go to continuum mechanical modeling, you will see the clear distinctions between them. But before going to continuum mechanics, let us make a thought experiment for a few systems. So if we think of a simple queue for some service, for example, or a radioactive sample, what would be the state variables for these systems? What would be the sources, sinks? What would be the flows for this kind of systems? And I would recommend you to think about this for a while and maybe pause the video for that. So if you want to pause, now is the right time. So let us return to the service queue. A natural state variable for a queue is the number of items in the queue. It's clearly a discrete state variable because it's an integer number. For inflow and outflow, the natural candidates are the items entering the queue, which is the natural inflow, and items getting to the service that is queued for. So they exit the queue in the normal order. It's not very easy to think reasonable source terms for a queue. So things are not normally inherently increasing within the queue. So queuing people do not reproduce in the queuing time. But a sink term can sometimes be meaningful. For example, if you are modeling a queuing situation where part of the queuing items are not patient enough, so they give up queuing without being served, and they disappear from the system, and that can be modeled as a sink term of the queue, especially if the rate of lost items is proportional to the volume of the queue, so the number of items in the queue rather than individual waiting times or so. As such, this is a very crude model for a queue. It only models the mass balance. It gives no information whatsoever about the actual internal structure and dynamics within the queue. So it's the same model for normal first in, first out queue, or last in, first out stack, or any more exotic data structure that can be used to sort incoming and outgoing stuff. So this much for a Q. About radioactive sample, the simplest models is that the state is simply the amount of radioactive particles denoted by R. So we are just counting particles, or particle density if needed, so depending how we want to do it. Mainly particles. So it's in some sense analogous to queuing, except that the amounts are now more or less astronomical, so typically millions, billions, and so on. So individual particle is of less importance. Particle flow is typically zero, so we have an isolated sample where no new particles are entering or no particles are lost through system boundaries. Also, the source term is zero, so no new radioactive particles are created, or at least not the ones that we are interested in. So the source is zero. The sink term is caused by radioactive decay. So the sink is proportional to the amount of radioactive particles in the system at a particular time. And the rate is the rate of radioactive decay. So it's basically the inverse of the halving time of radioactivity. So characterizes the lifetime of radioactive particle in some way. This leads us to a differential equation, a simple model that defines the rate of change of radioactive particles as a function of the current amount of them. This is a very simple model, and for example, if we think of C14 specimen, it's as itself, it's not enough to determine, for example, the age of the sample, which is the typical use case, because we only can observe R and its decay. So basically we can observe R and C at a certain time, but we have no information about the initial values, so how long the process has been going on, and so on. So we can refine the model and introduce the reaction products to the model. So we model the reaction of R dividing to A and B and emitting some neutrons N. A and B are reaction products. And then we have three conservation principles. So one for the original radioactive particle R, which is the decay equation. And then for A and B, we have source terms that arise from this radioactive decay. So they are the sources of A and B are proportional to concentration of R. And this reaction also produces neutrons. So we have a neutron flow, which is the actual measured radioactivity, which is also proportional to rate of transition of R to A and B. The system, we think, will not be able to capture significant amount of neutrons, so the neutron level within the system is constant. So the time derivative of neutron count is zero, and that basically tells that the neutron flow out from the system is equal to the neutron production rate, to the source term. And now we have more variables to decide about, for example, of the sample age, so how long the radioactive process has been going on. But these are just simple thought experiments. So, to summarize, or what is the goal of this lecture is we want to discuss continuum mechanical models, understand the general structures of continuum mechanical models using system approach and conservation principle as a guiding framework. We have been discussing already about systems and conservation principle on a very informal level. We will briefly go through some mathematical tools that are needed for modeling continuum systems. Once this is done, we will use them to formulate conservation laws in mathematical terms. Once this is done, we will also discuss continuum mechanical, actual physical conservation laws. And after that, we go to some examples. So we return to this balloon case, basically discuss various aspects of it. And after that, we will dig a bit deeper to thermodynamics to see that there's more of that than what we can explore in this short lecture. And finally, we summarize the main findings.